Hey folks, for the next video in 7.2, we're going to talk about energy. Now again, there's not really much new stuff to talk about, but we are going to focus on the graphs that we've learned about in the last video. So we focus on spring and pendulum oscillations because spring oscillations are caused by either just the spring force or a combination of spring and gravity. And then a pendulum oscillation is just caused by gravity. Those are our two conservative forces, and so under most circumstances, the total mechanical energy is constant. If there's friction, we can deal with that, and I'll show you at the end of the video what that might look like. There can be other non-conservative forces, like you could deal with a collision during an oscillation, and that would obviously change the energy. But when we're just talking about things oscillating, mostly they do so without any friction. So what that means, instead of saying like initial potential energy equals final kinetic energy, we can relate the maximum values of both to one another. And each of those maximum values is going to represent the mechanical energy in the system. Because when the spring is fully compressed, the block won't be moving. And then when the spring is fully extended or at equilibrium, the block will be moving very quickly. So there are moments where there is one type of energy and not the other, and that oscillation happens between them. So if it's a pendulum, then it's an oscillation that changes in height. And so the maximum gravitational potential energy is going to be mg times the maximum height. And then the kinetic energy is going to be 1/2 m times the maximum velocity squared. So there can be more complicated problems where you're analyzing the energy in the middle of an oscillation. But if you're focusing just on like the total energy in the system, you can either use the maximum potential energy or the maximum kinetic. For a mass spring oscillator, I don't go into the derivation, but regardless of the way the spring is oriented, it could be a horizontal spring or a vertical spring, we actually we are allowed to only consider the elastic potential energy. We can also consider the gravitational energy, but because of the symmetry and, again, a derivation I don't go into, we're actually allowed to ignore the effects of gravity in energy and only think about the elastic potential energy. In other words, the maximum elastic potential energy is 1/2 times the force constant times the amplitude of the oscillation squared. And then again, the maximum kinetic energy is 1/2 m times the maximum velocity squared. So in the rest of the video, I'm going to go through the graphs of energy, look at our maximums and our zeros, and then talk about what's called a damped oscillation. So here's our position graph from the first video, and we're going to take a look at Desmos real quick for that first energy graph. Okay, so I took the sine function that we had. I set it to an amplitude and a frequency so that we could see one complete cycle and not much more. And I added some formulas. Now I'm going to do this in kind of a funky order, and I use Desmos just still like kind of a basic user here, but I used Desmos so that I could show graphs of kinetic energy and gravitational energy. And so if I were to take this kinetic energy function and show it, it would look like this. Now, a couple of things that are really neat happen. Nothing's in the negative, and that's because kinetic energy depends on velocity squared. And so anytime you square velocity, even if it's negative, you get a positive value. So the lowest possible kinetic energy that something can have is none. And then as long as it's moving, it has some. And then you get some pretty clear relationships here. Like when this object is at equilibrium, that is when it has the maximum kinetic energy, because that is when its speed is at the greatest. If I then add in the potential energy, and I'm going to hide the position graph, you can see this relationship. As the kinetic energy goes down, potential goes up. If I show the position graph again and just show potential energy, I can see that the potential energy is at a maximum when the object is at the amplitude. So let's go back and draw those graphs and review those maximum and minimum values. So kinetic energy When the slope is at the greatest, that is when the kinetic energy is at its maximum. So that's at a time of 0. That is halfway through the period of oscillation. And then that is all the way at the end of the period of oscillation. And so the other things that happen is at the amplitudes, that's when the object is not moving, and that's when we have a 0 kinetic energy. So we have this oscillation. And what's kind of crazy about that is that the period of kinetic energy oscillation, which isn't really a thing, is half. That cycle is cut in half, where you go from maximum to maximum in the time of half a cycle. And there we go. Now that sets up something very important. We talked about maximum kinetic and maximum potential energy. This line that I'm going to draw, which is at the peaks of this graph, represent the mechanical energy. And I totally did not draw a flat line, but it's close enough, and you're going to believe me that this line represents the mechanical energy of that system. Now, what that means is when I go to my potential energy graph, that I can draw that same line, and that will also represent the mechanical energy. If it's the same system, nothing else has changed, then the mechanical energy is still the same. And so the potential energy graph is going to hit all those same maximum values. Okay, now I could draw this potential energy graph just as the flip or the inverse of the kinetic energy graph, but I'm going to go back to the position graph. When the position is at the amplitude, that is when we have the highest values of potential energy. So I'm going to plot those points right now. And then when the object is at equilibrium, that's a displacement of 0. And so no matter what type of potential energy it is, that's 0 of it, 0 potential energy. So we get a function that looks like this. Same deal, it has a period, or it oscillates at twice the rate as the position graph. And so we get that's not a half a period. We get 2 cycles of potential energy for every 1 cycle of the object. All right, to review, for kinetic energy, the maximum kinetic energy is at equilibrium. Now, I will ask you about forces again when we go into class and talk about this. So maybe you're thinking about, like, why would it be going the fastest when it gets to equilibrium, and what does that have to do with forces? And then kinetic energy equals 0 at the amplitude. For potential energy, it is the reverse. The maximum potential energy is going to be at the amplitude. And then potential energy is 0 at equilibrium. Now, the worksheets that I have in the packet are going to help you go through and review a lot of these things kind of at random. But it's always a good idea to just review these graphs and kind of know when you can see the maximum and minimum values of those quantities. Now, friction creates what's called a damped oscillation. So if there's a mass oscillating with a spring and it's sliding along a surface, there might be friction on that surface, and so that friction is going to reduce mechanical energy, and that has the effect of lowering the maximum velocity, and it lowers the amplitude. So in other words, it lowers every type of energy, and so you get less kinetic energy and less potential energy as the cycles happen. And it tends to be this decaying process. So there's this inverse relationship, and that would continue down to 0. The mechanical energy graph would be this nice smooth line because friction is gradually removing energy from that system. But the actual motion, let's say we started at our no kinetic energy, that graph of kinetic energy would have a constant period but the amplitude would just continue to get smaller and smaller. So kinetic energy versus time would look like that. Potential energy would be the inverse. We don't focus much on this type of oscillation, but it might pop up as like an extension on a question that you see on the exam. That's it.